So in part E now we need to use this newly found function to find the actual value of y when x is 5 pi over 12. So all we need to do is plug in 5 pi over 12 for x. So we find that this is 2.53. And in part 2, we need to recall that in the Euler's approximation, we found y to be 1.98. And why is this not accurate? So why is it so far? And well, we could say the step length is too small, which would be partially correct, but we could also look at the graph and see what really happens here. So if I write x times the square root of tangent x, then what we see in this region, we want to, if I zoom a little bit into x min, let's make 0, this should be pi over 2. Then we see, I mean, if we go to graph trace, we can go precisely to the value of 5 pi over 12 to see where we are approximating. So we see here that the gradient is very steep, and what Euler's method does is this linear approximation. So it approximates the slope of the graph through a straight line, and it always adds, that's how it always adds this y value. And we can see that the slope changes very quickly here, and Euler's method is simply not capable of following this quick rate of change. We would need a much smaller step length. So we could say something like gradient changes very rapidly. So it's not a good approximation. And then we need to state why this approximated is less than the actual value, and we need to consider that the curve is concave up, and so obviously the graph is going to grow at a quicker rate, so we will have a bigger value than what we approximate. So it's concave up. So it has to be larger.